Okay, thank you. Okay, we shall begin the class now. See what were we discussing? We're discussing the uh, properties of wireless estimators. We finished with um, small sample properties of these. The Gauss-Markov theorem tells you that the wireless estimator is the best linear unbiased estimator of all the class of linear unbiased estimators. Best in the sense it gives you the lowest variance in terms of the matrix. It is any other estimator is positive semi-definite. Okay, so the large sample properties, unbiasedness has the following two shortcomings. So the two shortcomings can be addressed by considering the large sample property, mainly of consistency, addresses the two shortcomings of unbiasedness. Large sample property, asymptotic properties of an estimator, or the properties of the sampling distribution of the estimator as sample size approaches infinity. It is not that sample size equal to or something like that. The small sample was the sample size can be anything, but it has to be less than finite. So we are interested in what will happen if the sample size approaches infinity, no matter what your the sample size of your applied experiment is. Such notions, actually, this is unavoidable. Actually, we talk about only asymptotic properties in many of the situations because you are not always on the comfort zone of wireless estimators, the comfort zone of what the classical linear regression model satisfies. It is invariable. That is an ideal situation. We are never in the ideal situation. So there'll always be some problem. The error terms, the assumptions concerning the error term may be violated. Assumptions concerning the X matrix may be violated, everything. There are a lot of other problems, functional form problems. So invariably, it is with asymptotic properties that econometricians talk about. So this is actually the rule rather than an exception. So nothing can be said without the assumption of very large samples by referring to consistency. As I said the earlier day, if you are suggesting a theoretical estimator, or if you are using an estimator suggested by somebody, make sure it satisfies at least the consistency property. Otherwise, dump it. Otherwise, don't even be in the business. So this is the general, the received wisdom of almost everyone. So this is the basic sine qua non, the fundamental property of any estimator, consistency. The basic wireless model, it is straightforward to derive the large sample or asymptotic properties of the least cost estimator. So when I say GLS, next we are talking about GLS. Suppose we start relaxing the assumptions of wireless and start recommending estimators, they will also be satisfying all this stuff. The only problem is the mathematics becomes very complicated from here onwards. Large sample asymptotic properties. You need to know a lot of limit theorems, convergence properties, and generally should be the vector matrix algebra also becomes very complicated. So where necessary, I'll simplify the arguments, and mostly I'll be simplifying the argument for large sample properties. No wonder theoretical econometrics is a difficult field to do research in. Okay, the second bullet point, we did not use the normality assumption as establishing finite sample properties, and it is in essential even to establish large sample properties. In fact, it is enough if you have some assumptions about the moments of the distribution. It's not necessary the distribution must be from some specified distribution, some particular distribution, because we are going to make use of CLT. But however, to make inference, and if you are interested in maximum likelihood
So, I think you're on mute.
Oh, I had muted myself by mistake.
Yes, sir.
Now can you hear me?
Yes, sir.
Okay. So the distribution assumptions are very essential to draw a statistical inference. Let's start with this consistency of least squares estimators. Here we have to know if the least squares estimator B is consistent and also if the least squares variance estimator is also consistent. So what do you mean by this? We begin by making two important assumptions. First is a modification of assumption A5, full rank matrix and all those stuff. We now allow the data to be stochastic or any mixture of constants and random variables generated independently of the error process. That is, of course, maintained. If you come out of that, OLS will not be, we have to make some other arrangements. We have to come to a different variance, a different system altogether. So A5A, X1, Xi, EI, I is equal to 110 is a sequence of independent observations where Xi denotes the elements of the ith column vector of X. Okay, this last bullet point is a very, very important assumption in asymptotics. Look at that. It goes to a positive definite matrix, which is and it is invertible also. So positive definite matrix. It should go to a constant, which is positive definite matrix. It should not explode forever.
So what is P-lim?
Probability limit. I'm just coming there. This matrix should go to some constant matrix, Q positive definite matrix. Okay. Okay, give me an instance when this could be violated. As n tends to infinity, this could be violated. This OLS 55. Okay, one clue is you're talking of cross-section data. It consists of cross-section data. Now tell me, so when will this assumption be violated? That it will converge onto some constant positive definite matrix. This is of course a symmetric matrix because it's a product moment matrix. Any idea? No. What will happen if my X consists of trending variables? What will happen to this assumption when my X matrix consists of variables that are trending? When I say variables that are trending, what type of data am I talking about?
Time series.
Time series data. Okay. Will this be satisfied or? Q is a finite positive definite matrix.
So then there will be autocorrelation then.
No, Drishan, my idea is the Q is a finite positive definite matrix. When there are trending variables, as n tends to infinity, will this be satisfied or
Yes,
not?
sir. It won't be satisfied. Like
It won't be satisfied. Okay,
can
this is the problem.
also go above
Yeah, this is
the
the problem.
rate of n. The rate
Yeah,
of growth of n.
in time series application, if there are trending variables in your X, then this will be violated. This is a huge area of interest in time series econometrics. So here is where the idea of how to treat trending variables. From here comes the idea of how to treat non-stationary time series and all those stuff. Those who are interested in knowing this, and this leads to another very important contribution in theoretical econometrics, which is called different asymptotic rates of convergence. So if you want to know more about it, read Hamilton chapter 16. Hamilton time series analysis chapter 16. You'll understand what I'm saying. So this will be violated. What should be done to correct the situation? Okay, so this is it. I'm not going to come back to this topic anymore. For us, this is sacrosanct. This must not be violated. OLS 55. You can even take it down. Now, what is PLIM? PLIM is nothing but probability limit. PLIM is a short form of probability limit. So in probability, random variable, a sequence of random variables will converge to that limit. So we write an arrow and a P above. So we will come there now. Some rules of probability limits are there. These are the rules. There are two more rules. There are two more rules. Down also if necessary. We shall list out two theorems that are useful to prove the large sample properties of the estimators. Just take it as a theorem. Shall not try to prove anything. The Slutsky's theorem. If pim theta is equal to theta, and if g theta hat n is a continuous function, then plim g theta hat n is nothing but a function of g theta.
Sir, can you
Yeah.
repeat what P-lim is? I couldn't finish that part.
What is it? Can you come again? Your voice is breaking.
Sir, can you just repeat the P-lim part? What P probability limit means?
Yeah, probability limit. Yeah.
Sir, what it means? What is like
Probability limit is nothing but where the limit or that a random variable or a sequence of random variables will converge to when sample size increases to infinity.
Okay, got it.
Okay, that is called convergence in probability. So this is a theorem. Look at this for example. I've given you an example. So probability limit of a continuous function is a function evaluated at the probability limit. Yeah, I should have had a slide explaining probability limit. How dumb of me. I'll before sending the thing to you, I'll include a definition of probability limit, some example also. Okay. I just presume that you guys would know me, but that's not a good thing. Okay, now this is it. The last bullet point is what you should know. Plane theta tilde is equal to sigma. Plane sigma tilde is equal to sigma. According to Slutsky's theorem, it does go to it is equal to the probability limit. So the probability limit of sigma tilde as n tends to infinity is just sigma, which is nothing but the population parameter. Oh boy, Kinchener's theorem. Every theorem can be proved, but just take it. Plim x and bar is going to just go through it. This theorem states that the sample mean computed from a random sample of independent and identical distributed observations will be a consistent estimate of the population mean. I think this some econometrics is there. This is nothing but weak law of large numbers. The sample mean converges to the population mean. We read this as weak law of large numbers. It's also a strong law of large numbers. For our purpose, what is this Kinchener's theorem thing? For our purpose, here it was xi is equal to 1 to n, x1, x2, xn. For our purpose, the IID random variables will be E1 square, En square as a random sample of IID observations, E1 square, remember? E1 square. So the population mean EI square equal to sigma square. So what do we have to prove? We have to prove that plim EI bar, plim that E bar E, this is nothing but the EI square bar. So E bar E by N equal to sigma square. So this is the result that we need. This is the result that we need. Kinchener's theorem can be proved, but it's not necessary here. We have seen Chebyshev inequality in the Markov inequality and all those stuff. With all the central limit theorem can be proved, but that is not mandatory here. You just know the theorem, that's it. IID random variable, the sample mean of IID random variables reaches the population mean. There it was just xi, here it is nothing but mean of EI square, which is nothing but sigma square, which is nothing but the variance. So this reaches the population variance. Expected value of E is, variance of E is nothing but expected value of E square. It's like that. With these results, we can show the consistency of OLS estimators B and the least squares variance estimator. Remember, okay, now go through it carefully. The least squares estimators may then be written as OLS 56. If Q inverse exists and it is a finite, I said it is a finite positive definite matrix, so it will exist. So, it is always mandatory to add the word Q in if Q inverse exists. Then plim B equal to beta plus Q inverse plim X prime E by N. Okay, before we proceed, what should we prove now? Given this, what do we have to prove now?
Plim B is equals to beta.
Correct. So for that, to prove that, I have to show
Plim X dash E divided by N should go to 0.
That's what I have to prove, isn't it? That's just so we'll start from there. The Q inverse exists, so it should not be 0. So I have to show that this goes to 0. See the gymnastic that we have to do. We require the probability of the last term in OLS 56. Okay, that is it. OLS 56. Okay, now let's see OLS 56.1. Is it okay? Kumar, are you there?
I'm there, sir.
Okay, so could you go through the previous slides, yesterday's slides?
Yes, sir.
Last class slides?
Yes, sir.
Any problem there?
No, sir. No, sir. Now it's fine.
Okay, now today are we slow, fast, or too fast for you?
Sir, it's good, sir.
What's the speed? It's okay. Okay, now go through it now.
Thank you, sir. Thanks.
Yeah, go through it now. Okay, let's ask about. Paul, Babu,
Yes, sir.
is it okay for you? Going okay for you?
Yes, sir. Comparatively better, sir.
Okay. Okay. Acha, these guys, who are the PhD guys here in this? Chitralekha, you are a PhD student?
No, sir, MSc student.
Who are the PhD students here? They're not there.
No, sir, we are here.
I can't tell. I can see who is it?
Sir, Yashika this side.
Yashika Gupta, Yashika Chub.
Yes, sir, yes.
Okay, how do you, I mean, there's some, okay, I have to ask you some question. You have to, I'll treat you as a representative of the thing, of a PhD student. How is it go? You find it very fast or difficult, or how do you find this course so far?
The course is fine. The problem is the time. Actually, when we have like exams or the midterm, so we are not able to. We can attend the classes, but we are not able to revise the previous like slide. So then there is a lag between like you and us. So that creates problems sometimes. And
But I've been sending the slides almost immediately after the class, except on one occasion. The problem in going through the slides is because you are not able to download it, or is because of the difficulty level?
no, sir, no, it's not about the difficulty level.
Yeah. Yeah, somebody else is just saying that. Who is that?
Yes, sir, Anas.
Yeah.
Sir, we have a time constraint. Sir, we have every other day we have assignment, then meeting, then mid-sem, and then classes, regular classes we get only 1 day off.
Okay. So it is not the difficulty level or the course, the speed at which it is being delivered or something like that. Nothing to do with the course, I suppose. At least my course. Hello, Anas?
Yes, sir. Just that it is too much for us to go through in a short time.
Okay. But the slides are as self-contained as they can be. Can you say that?
Yes, sir.
No, you can tell me if something needs to be done to fill up the gap. I'll try to do that.
We PhD, all students will discuss and let you know.
Okay. Okay, continue. Okay, now we are OLS 56.1. So I have to show that the left-hand side in plim goes to 0. In other words, I have to show that W bar goes to plim W bar. I discuss plim W bar. Then plim B equal to beta Q inverse plim W bar. From the exogeneity assumption A3, we have EWXI is equal to, again, unconditional expectation is the expectation of the conditional expectation, which is equal to 0. Is it okay? So that expectation of EW bar equal to 0. For any element in Xi that is non-stochastic, the 0 expectations follows from the model distribution of E. Yeah.
Sir, once can you scroll up a few slides?
Previous slides?
Yes.
Previous slides?
Yeah, okay. Sir, so in this one, you have said that P-lim X prime E by N that tends to 0. But
should tend to 0. That should tend to 0.
Yes. And we have shown that the expectation of this thing tends to 0.
Yeah, but now for some we have to remind, we have some more results I have to show.
Oh, okay.
Okay, now the expectation goes to 0. Now for any element of non-stochastic, 0 expectations follows the model distribution. Consider the variance now. This is something I have seen before. I had, when we were discussing covariance properties, this was one of the results that I had displayed. I think if I remember right, I don't know which handout. I'm taking that from that handout. So this is a result. Given this result, we can write the variance in the present case var w bar equal to this. The second term is 0 because expectation of EIX equal to 0. Why did I say that?
Sir, can you repeat the question? What did you say?
What is the third bullet point? Why am I saying so? The second term is 0.
Because covariance between error and deterministic term is 0.
No. What is the variance formula?
Sir, we are using Eve's law here to find the variance, right?
Right. What is it? Simply variance formula kya hai? I'm saying the second term in the second bullet point will be 0. Why?
Variance of anything which is 0 is 0. So it will like because W bar is 1 by n summation EIXI. So in that case, so EIXI summation EIXI given x, and then we find out the expectation, and then we get the whole thing as as 0. So in that case, I think the second term will be 0 if I'm not wrong.
Okay. Now you have to simply apply the. You have to simply apply. Yeah.
Sir, that expectation of W bar given x, that thing can be written as expectation of xi given expectation of ei given xi, and so that part is 0, and as a whole that thing becomes 0.
Yes, expected value of this. What is variance formula of x? Var x is equal to expected value of x minus expected value of x whole square, isn't it? So here is nothing but expected value of this minus expected value of expected this. According to law of iterated expectation, both expectations will be the same and they cancel out and it is becomes 0. The variance of 0 becomes 0. So we are interested only in the first term now. To obtain the first, we use this sigma square I, so that var w bar x equal to this. Go through this. Now, Drishan, can you guess where I am going? Given this result, 55, very important. I will be coming to 55 again and again and again. Can you guess where I am going?
So P lim of that becomes
yes. Now, that's what I'm going. See, for example. Therefore, var w bar equal to sigma square n expected value of, because remember, I'm just evaluating this inside term, so the expectation remains. So expected value of x stands for x by n. The variance will collapse to 0 if the expectation in parenthesis is or converges to constant matrix, so that the leading scalar will dominate the product as n increases. So what do I mean by this?
Sir, the expectation, that part is Q, that second part,
Yeah.
and as n tends to infinity, the sigma square by n part tends to 0, and so
Yeah, that will dominate. As of now, that will dominate as n increases. That is, the scalar that I'm referring to is nothing but sigma square n. Okay, let's see. So
Sir, just
yeah.
a minute. Can you go to the previous slide? Okay, sir. So here you're taking expectation of variance of W bar given X.
I don't know. This is only var W bar. I have shown that var W bar is equal to this. This slide I'm taking expectation.
Okay, but the previous one is var W bar given X.
Yeah, that is what. So I'm taking only var W bar. Now expectation remains. I'm taking the expectation here.
Okay, yeah. Okay,
oh,
sir.
I need a E here, right? I need a E here. Paramila.
Yes.
I need a E here on the left hand side. Am I right?
Yes, sir. Exactly.
Okay, that is missing. Okay, I'll correct it. 186. Okay. The variance will collapse to 0. The expectation in parentheses is a converges to constant matrix, so that. Okay, now, so by OLS 55, then limit n tending to infinity, can we say this var W bar, limit n tending to infinity var W bar will be 0 into Q dot 0. What is that noise here? Since the mean of W bar is identically 0 and its variance converges to 0, okay, now W bar converges and mean square to 0, so the plim W bar is therefore 0. So plim X transpose E by N equal to 0. Devesh?
Yes, sir. Yes, sir.
This is what we wanted to prove, remember?
Yes, sir.
Okay, so plim X bar, so that plim B equal to B plus Q inverse star equal to B, while as 55. This establishes that under assumptions A1 through A4 and the additional assumption A5, B is a consistent estimator of beta in the linear regression model. So for consistency, you have to show that as n tends to infinity, this is the probability limit. The limit to which the OLS estimator B will converge to is the population parameter beta. That is the whole thing. Forget all the proof. This is the only thing that you have to remember. The concept that I have used here can be very good to, it can be very useful to remember. But what you need to know when I talk about consistency is there is an OLS 58. Plim B equal to beta, whereas for unbiasedness, expected value of B equal to beta. That is the only difference. Unbiasedness of small sample properties or exact finite sample properties from the name itself is for any given sample. The sample size can be anything, but here it's not that. We start with some reasonably small sample only. So we are interested in knowing what will happen to our estimator. How will our estimator behave? This ends if the sample size tends to infinity. Okay, we hope that if n tends to infinity, our estimator in the probability limit will converge to the population parameter beta. That is the whole idea of the so-called asymptotic or consistency property of the least squares estimator B.
Sir, I have a question, sir.
Yeah.
In statistics, we had learned that the sufficient conditions for the consistency of estimators are that the expectation of that estimator tends to the as n tends to infinity, the probability limit of that estimator tends to the I mean to say the parameter, and that the variance will tend to 0 as n tends to infinity. So here we need to prove that the variance of the estimator also tends to infinity, it tends to 0 as n tends to infinity, or we use some other definition here.
You know what is that? Just wait. I have just only show that B equal to goes to the mean. Beta is the mean or the variance.
Yes, yes.
Okay. The reference point is always the undergrad notes, is it?
No, sir, I was connecting it to the statistics we had learned in undergrad. So that is why I was a little confused. Like, are we doing the same thing, or are we doing the something else? So
No, that estimate, that's slightly different. Okay, I'm just coming there. Okay, for
Okay.
now, is it okay? OLS 58 is okay?
yes, yes. Okay.
Remember, I'm talking about only consistency of what is that? So B square consistent, the least square variance estimate is also consistent. Remember, the second bullet point remains.
Okay, sir. Okay.
Okay, now OLS 58 now. Okay. Now, what is an asymptotic distribution? What is a distribution, Kanika? Suppose you say random variable is normally distributed. To quantify the distribution, what are all the quantities you need? Do you need?
The moments.
Normal distribution is completely characterized by two parameters, the mean and the variance. Correct? So that is that. So the distribution, then you say the distribution is complete. Now you see, start from there. What is an asymptotic distribution? To answer that, we need to know what a limiting distribution is, because it is the limiting distribution that is the means to derive the asymptotic distribution. Unfortunately, in statistics books, in many statistics book, and in econometrics book, this definition is most of the times blurred. Even famous econometricians, statisticians, they do not try to differentiate between a limiting distribution and an asymptotic distribution. Okay, let's see that. But limiting distribution, they are correct in the sense, one limit, the moment you derive the limiting distribution, you can use the other theorems like mean square convergence, Kenchinese theorem, CLT, to show that it is asymptotic distribution. After some experience, you can always write the asymptotic distribution given the limiting distribution. Okay, so they are not absolute, they're okay to avoid the notational confusion, we'll be using it, but there is a subtle difference between these two. We will see that. Limiting distributions are obtained through the central limit theorem, and that involve the unknown parameters. Central limit theorems involve the unknown parameters. Those unknown parameters are the ones we are trying to estimate. Okay, and central limit theorem assumes that the sample size tends to infinity. Our sample sizes are always finite. So we depart from the limiting distributions to derive the asymptotic distribution of the estimators. Go through it. But we have to add here that many authors do not differentiate between limiting distributions and asymptotic distributions. So in practice, in econometrics, you always talk about asymptotic distributions or limiting distributions. What have you been taught? Asymptotic distribution. Asymptotic distribution is a distribution that is used to approximate the true finite sample distribution of a random variable. This is the definition. Before we go further on the asymptotic distributions, we shall recall the small discussion on convergence in distribution in the statistics portion. Convergence in distribution, asymptotic distribution. This is what I had given you long before in your statistics. The last bullet point is something we had seen before.
Sir, can you please explain the difference between asymptotic distribution and limiting distribution? I couldn't understand properly.
Just wait. Asymptotic distribution continued. By far, the most common means of formulating an asymptotic. Look at that. What is the definition of asymptotic distribution? Asymptotic distribution is the distribution that is used to approximate the true finite sample distribution of a random variable given your finite sample, given your sample. Okay. You want to know the exact or true finite sample distribution, that is asymptotic distribution. The limiting distribution tells you what will happen to the distribution if n goes to infinity. This is the.
Oh, okay, sir.
I'm just giving the example that you will make it very clear. What is the difference and what we do? Okay. Asymptotic distribution continued. By far, the most common means of formulating an asymptotic distribution, at least by econometricians, is to construct it from the known limiting distribution of the random variable. Second bullet point, you are all very familiar with that?
Yes, sir.
So when you are working with some finite
Standard
normal. So when
standard
you are
normal distribution of the sample.
Yeah, we have seen this before, even how to derive this in the statistics portion.
Sir, this is actually central limit theorem because sample mean is normally distributed with mean mu and variance sigma by root n. Now you have standardized it.
Yeah, but what did I say? Limiting distribution always relies on central limit theorem. It always tells you what will happen to the random variable when n tends to infinity. Am I right?
Yes, sir.
Yes, sir. For any arbitrary.
Now what we are in practice, we have only finite sample. So if you want to comment on the distribution of the random variable when you have finite sample, this is asymptotic distribution is what you should be using. That's what I mean. Now you understand, Kanika?
Yes, sir. Yes, sir.
Okay, the limiting distribution is all theory. This is where it will go to. But in practice, we will be using the asymptotic distribution. To pass and to calculate the standard errors on x bar n, we'll be using sigma square by n. Sigma square is still mu has to be replaced with something. Sigma square is still a population parameter to find the estimate of a sigma square. That is what we'll be using.
So that means limiting distribution is always followed from CLT and asymptotic is not the case. Like we cannot.
No, it's not the case. नहीं, limiting distribution से ही asymptotic distribution आता है. But in between there is a theory. I'm just coming to that. It's not that limiting distribution has to be given the go by. No. From limiting distribution we come to asymptotic distribution. You get my point? From limiting distribution, how do we come to asymptotic distribution? It's very simple. By looking at it, you can see.
Sir, the limiting distribution of root n, that x bar minus mu by sigma, that follows like standard normal. And when we take the small sample case of that, then asymptotically we can say that x bar follows normal distribution with mu and sigma square n, like right, for small sample.
See, for example, take the asymptotic x bar n is asymptotic distributed mean mu and sigma square n. What will be now? What will be the distribution of root n x bar n?
Root n normal root n mu comma sigma square.
Anna. So what have I done here in the limiting distribution?
Sir, I think difference is very simple. It's just a matter of saying infinity and finite. I mean, as n tends to infinity.
Exactly. That's what I'm asking you the question. I given you X bar n distributed, forget the word asymptotically, distributed as normal, mean mu and sigma square n. Suppose I ask the next question, what will be the distribution of root n X bar n? You said root n mu to sigma square, isn't it? Now find the distribution of X bar n minus mu by sigma or whatever it is. You'll see what happened. You'll get distribution of, it's a standard normal distribution only. So the only difference between limiting distribution and asymptotic distribution is limiting distribution is for the behavior when n tends to infinity. The asymptotic distribution is just for a finite sample. For inference purposes, what do we use? We use the asymptotic distribution. That you must have definitely heard of, all those who have done econometrics or statistics, haven't you?
Yes, sir. As n becomes larger and larger, the asymptotic distribution itself will tend to the limiting.
For example, if n becomes larger, what will happen to the asymptotic distribution here? What will happen to X bar n?
It will go to the limiting distribution.
The population mu, X bar n will go to population mu. If it
X
reaches
bar n,
population mu, what will happen to the variance?
10 to 0.
Correct. Yeah, that is it. That's the whole idea. Can we go to the next slide?
Yes, sir.
Sir, I just need to clarify one last thing. So, sir, for a large sample or like when n tends to infinity, that case we use the definition of a limiting distribution, and when it is a finite or small sample case, we say that we say asymptotic distribution, right?
Correct. So limiting distribution is a sort of an ideal distribution. That is our goal.
Yes, when n tends to infinity.
When you are working with any finite sample data, we refer to only asymptotic distribution.
Yeah. Okay.
Okay. But theoretical guys will say this goes to as n tends to infinity because that is important. In n goes to infinity, this, when it comes to practical thing, which one they will be referring? They'll be referring to asymptotic distribution. That's the whole idea. So all inferences are done only on the asymptotic distribution. The statement X bar n is asymptotically normal distributed mean mu and variance sigma square and says only that this normal distribution provides an approximation to the true distribution and not that the true distribution is exactly normal. Remember, it's an approximation. Asymptotic distribution provides an approximation to the true distribution, but not the true distribution is exactly normal. Extending this definition, suppose theta hat n is an estimate of the parameter vector theta. The asymptotic distribution of theta hat n is obtained from the limiting distribution. Now you tell me, what will be the asymptotic distribution? You write the asymptotic distribution. I've given you the limiting distribution. Now remember some vector, parameter vector. That was square because it is a scalar. Now write the asymptotic distribution.
Sir, is it theta n hat follows normal theta comma v by n?
1 minute. Remember, this is a vector and V becomes a matrix. What will happen now? It implies that
1 by n. Yes.
Okay. Now the difference theta hat n is normally distributed asymptotically is mean theta and 1 by n V. Okay, Paul, do you follow this? Paul, where is Paul? Babu?
Yes, sir. I'm here, sir.
Do you get this simple difference, subtle difference between the limiting distribution and the asymptotic distribution?
Sir, I'm trying to read this. Just a minute.
Where are you? You're not watching the screen.
So the difference between, okay, there's a D on top of tends to, and
that is convergence in that is a nomenclature. Is it formula?
yes, sir.
Convergence in distribution. This is asymptotically distributed. That's it.
Okay, sir.
No. Okay. Now, if I can use this word, that is the ideal. That is the, let us say, true distribution. I don't know whether I can use this word. This is a true distribution, and this is for the given finite time distribution. I don't know whether I can use the word because that is here approximation to the true distribution. Not that the true distribution is exactly normal. This says it's not true distribution. Hopefully, when n tends to infinity, this fellow asymptotic distribution will go towards the true distribution, the limiting distribution. Can I say that?
Yes, as n tends to infinity. Yeah.
Yes, as sample size increases. So this is according to the central limit theorem. This is what we are. This is our goal. From here we have come here because we always work with finite samples. Okay, let's see. Chitralekha, I have not talked to you for a long time. How do you find this?
I am trying to catch it up, sir.
Okay, I mean the slides so far, the previous slides had some finite sample properties. Those slides are okay.
Yeah, sir. I mean, like sometimes I have some network issues, so the slides stop at my part. But
why don't you? Acha, okay, download
yeah,
it. Okay,
it's from my part. Sometimes it happens.
Okay. Let's talk about Ritika Paul. Ritika, how do you find this? Ritika?
Sir, I'm trying to cope up, sir. With
why? What is the problem, Ritika?
no, sir, no problem, but things are a bit difficult. So
the difficulty level of tell me.
Yes, sir. So I'm trying my best, sir.
No, the slides are self-contained. You have problems with the slides?
No, sir. The slides are okay, sir.
Okay. It's only a question of get the time to rewind it. Is it revise it, right?
Yes, sir. Yes, sir.
Okay. Pooja Mahato.
Yes, sir.
How do you find this?
Yes, sir. It's fine.
You are a PhD student or MSc student?
MSc student.
I have to make sure who are PhD and who are the PhD students here. You tell me. Who are the PhD students? Anas Khan is there, and Yashika is there. Others?
Sir, Sonali this side.
Sonali Goel. How do you find this?
Sir, it's fine. Basically, again, as Yashika mentioned, that we are not getting time to revise it. But yeah, it's fine, and the slides are very good.
Okay, good. Okay, now we have to go to the next thing. Since the covariance matrix of the asymptotic distribution is the asymptotic covariance matrix and is denoted by this. Asymptotic covariance matrix of theta hat n is equal to 1 by n v. I have written it from the previous expression. So the inherent logic is that while limiting distribution holds exactly when n tends to infinity, we assume it holds approximately for finite n when we talk about asymptotic distribution. Okay, all this bullet point explains as simply as possible the difference between limiting and the asymptotic distribution. Kanika, Drishan, Paramila, Kumar, is this bullet point okay?
Yes, sir.
Kanika?
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir.
It holds approximately for finite n when you talk about asymptotic distribution. This is the subtle difference between the limiting distribution and an asymptotic distribution. So have it in mind. Asymptotic normality of the least squares estimators. To derive the asymptotic distribution of the least squares estimators, B, we shall derive its limiting distribution first. We shall find in this section that to derive the asymptotic distribution of the least squares estimator, we do not need the assumption of normality of disturbances. That's why I put a question mark there, exclamation mark there. We need to only assume that assumption A3 of uncorrelatedness and that the disturbances are independent. Then it follows from OLS 56 that this is OLS 59. You need OLS 56, then where it is? Oh, we know this. So I have to write, I've written it. I had written it in deviations form and some adjustments. Since the inverse matrix is a continuous function of the original matrix we have from QLS 55, we had only thought about x transpose x inverse equal to Q, and we also say from plim of x transpose x inverse is equal to Q inverse, so that the plim of the first term will be Q inverse. If the limiting distribution of the random vector in OLS, what is the random vector? X transpose E, then the limiting distribution is same as that of, okay, look at that, OLS 59. If the limiting distribution of the random vector exists, then that limiting distribution is the same as that of the left-hand one, as this. OLS 60. We must establish that the limiting distribution of this equal to 0. Hello, Kanika, are you coming there?
Yes, sir. Yes, sir.
What is this now, the last term? Hey, there is some problem here. What is this root n equal to? No, this is a problem here. OLS 61, there is something missing there, but this is the limiting distribution. So we have to show that this is equal to 0. I think this must be root n W bar. OLS 61, there is a typo. Okay, we can use a multivariate Lindbergh-Feller version of the central limit theorem. We have not seen this. Acha, where is this guy? Shaurav. Saurav is not there. Saurav Kumar?
Sir, I am there.
Okay. Okay, now we are using the multivariate Lindbergh version, Lindbergh-Feller version. We had not seen this. We had seen only one version of the central limit theorem, that is the univariate Lindbergh-Levy version of the central limit theorem, which is for IID random variables. We had just mentioned the univariate central limit theorem, which is called the Lyapunov version for only independent variables, for random variables, so the random variables are not necessarily identically distributed. Okay, that was extended to the multivariate version by Lindbergh and Feller. That is, Lyapunov version was extended to the multivariate version by Lindbergh and Feller. This is extremely difficult mathematically. Also, yeah. So anybody who wants to know the intricacies of how we arrived at it, you must have definitely heard about the book by C.R. Rao. Have you heard about the book by C.R. Rao?
Yes, sir. He was in ISIS, I
Yeah,
suppose.
his book has the proof of all that I'm saying, the Lindbergh filler, but this is very difficult, let me tell you. So we'll just forget it. So we'll say we can use a multivariate Lindbergh filler version of the central limit theorem, which allows for not identically distributed random variables to obtain the limiting distribution. Yeah, this W bar should be there, I'm sorry, in 61, root and W bar. Using that formulation, W bar is the average of n independent random vectors. Wi is equal to xi ei with mean 0 and variances while 62. This is nothing big, you can just go through it. Remember, the independence is very important to derive this variance. That is why I'm taking the sigma square out and the expected xi transpose is inside, sigma square out and qi. Okay. Now variance of, hence the variance of root n w bar is sigma square q bar n, which is nothing but sigma square into q1 plus q2 plus qn, as long as the sum is not dominated by any particular term and the regressors are well behaved, which in this case means OLS 35 holds. Okay, now whoever said about the Q matrix, what do I mean by this, Paramila? Given the situation, it will not be dominated. Why I'm saying so?
Sir, earlier you had talked about plim x dash x by n. That
OLS 55, I had asked you to take it down. Plim n tends to plim x times with x by n goes to q, isn't it?
Yes.
Equal to q. Okay, now I say that q will not work. That identity will not work if q contain trending variables. Now you
yes, we need a stationary series.
Yeah, basically for stationary series, correct. Okay, there are trending variables that will not work. As long as the sum is not dominated by any particular term and the regressors are well behaved. This is what I mean as regressors are very well behaved. And the sum is not dominated by any particular term, meaning no q takes off. It will take off in the case of trending variables. As n tends to infinity, they also will tend to grow. That's what I mean by not dominated by any particular term. It's all around the same thing, some ideal q, which in this case means OLS 55 holds. So limit n tending to infinity, sigma square q bar n equal to sigma square q. That means to say all q's will always go to some limit, okay, which in this case all q bar, all q inside will go to some limit q, so that as n tends to infinity, you are going to say that q bar n goes to the limit sigma square q. Therefore, we can apply the Lindbergh-Feller version of the central limit theorem. This is a bit too much, of course. We have all the ingredients to obtain the desired result. What is this? If xi, I is equal to 1 to n are independent vectors distributed mean 0 and variance sigma square qi less than infinity, and if OLS 35 holds, it follows that q bar n is this. Combining terms, we get the limiting distribution. That we can write the asymptotic distribution as this. OLS 65, OLS 66. Now you tell me, in practice, what do we do with OLS 66? Q is the limit. In practice, what do we replace with?
Yes, sir. That would be the variance of. No,
So,
not the variance.
sir, will it q is equal to, we know that q is equal to expectation of x prime x by n.
Exactly.
So,
that is
q
what we'll
yes,
replace it
and
with x transpose x. X transpose x. Am I right?
Yes.
Now that is it. Now OLS 66. This implies that. Now, do you understand? My only question is, do you understand when I come from 65 to 66? That is my only question.
We're coming from limiting to asymptotic.
That is the limit to asymptotic, yes.
Yeah. Is that okay?
Sir, I just have one question. Like this entire proof that you did, is it very important for us to remember this procedure?
No. The last 2 bullet points you remember.
Okay.
Last 2 bullet points you remember. This is for completion of the class. I'm giving you a completion of the proof. I'm giving you all this stuff. I was about to say that, Drishan, you asked me. I was about to tell you that the properties you remember, and this important difference between limiting and asymptotic distribution you remember. Okay?
Yes.
Given the asymptotic distribution, you can always write the limiting distribution, correct?
Yes, sir.
Suppose I tell you this is asymptotic distribution. I ask you a question. What will be the distribution of root n b?
Then it will follow normal distribution with a mean root n beta and variance sigma square q inverse.
Yes, that is exactly. This is exactly rewritten. I have just taken the root n b to the left hand side and written the distribution, limiting distribution. Do you understand now?
Yes, sir.
Okay, that is exactly the difference between limiting distribution and an asymptotic distribution. Never ever do I claim that these two are different. No, limiting distribution leads to the asymptotic distribution. I'm not saying that there are weak law of large numbers, Kinch-Innes theorem, CLT involved in coming from OLS 65 to OLS 66. I never claim that this is not important. Limiting distribution is our ideal. Okay, so we cannot reach the ideal. So what is the next best thing? Concentrate on the asymptotic distribution. And as this sample size goes to infinity, we'll slowly reach the limiting distribution. That is the whole idea. That is the root. So I'm not diluting the importance of limiting distribution. That is the ideal. And this is the path. Okay, this is where you have to work with given the sample size. So do not think otherwise. The limiting distribution is not important. I'm not saying that. But what is normally reported is the asymptotic distribution. In practice, it is necessary to estimate 1 by nq inverse with x transpose x inverse, and so sigma square with E transpose E by n minus k. E transpose E by n minus k. Now we shall check the consistency of S square, which we know as the estimate of the disturbance variance sigma square. What is it? To use OLS 56, we need only show the proof. We only need to show that S square, which is an estimate of a sigma square, is consistent. Consistency of S square, the estimate of asymptotic variance of B. To complete the derivation of the asymptotic properties of B, we will require an estimate of asymptotic variance of B, sigma square by Q inverse. With OLS 55, it is sufficient to restrict attention to S square only. That is, we need to assess the consistency of S square as an estimate of sigma square. Expanding this, boy, this leading constant clearly converges to 1. Can we say this?
Sir, how did we get to the third point?
Remember your previous lessons, what is ME? What is M?
M is 1 minus X transpose.
Where is 1 minus? Where is 1 minus? That is a matrix. Remember the idempotent matrix?
Yes, okay, I got it. 1 minus X. Yes, sir. Yes, I got it.
Okay, we should show extra results. Mx is equal to 0, Me equal to E. Okay, so I'm going to say E transpose Me, and we get this. The last bullet point, the leading constant clearly converges to 1. Is it okay?
Sir, how? I'm not getting it.
What is the leading constant here?
Huh?
Leading constant?
Sir, in which one?
In this expression, the last equality?
E prime E.
No, leading constant. N by n minus k.
N by n minus k.
So that converges to 1?
Yes.
Can you say that?
Yes.
Okay, now that's what I want.
No, sir, I'm asking like the thing in the bracket.
No, I'm just coming. Okay, so we can apply OLS 55 and OLS 57 and the product rule for probability limit to assert that the second term in the brackets converges to 0. The second term in the brackets. That leaves can we say that this second term converges to 0?
Yes, sir. We put P ln x prime E by N is 0.
Yeah, can we say that? I have used the product rule for the probability limits. Drishan, can we say this second term in the square bracket converges to 0?
Yes, sir.
Correct. So that leaves us with the first term, E transpose E. This the first term within the square bracket. Now here I'm going to use a theorem. What theorem that you have seen so far, that you have seen in this?
The Kingenis theorem.
Uh-huh.
Kingenis theorem.
Yeah, but who is this, Devesh?
No, sir, Avik.
Avik, is it okay from this bracket, square bracket, and you come here?
Yes, sir.
Okay, what is this term? This term refers to which term in the square bracket is this expression? The second bullet
first term. The first
term within the square bracket. Okay, now this is a narrow case, and under fairly weak conditions, this converges to sigma square, that is under Kingenis theorem, so that the first term within the square bracket converges in probability to sigma square. This gives the received result plim S square is equal to sigma square. Drishan, is it okay? Kanika, Pramila, Kumar, others?
Yes, sir.
Kumar,
Yes, sir.
Kumar, how is it going today? Very fast, or is it okay?
No, sir. It's perfectly fine. Thank you, sir.
Okay.
It's very good. Last time it was a bit fast. Now it is completely all right.
Okay. Nilesh. Nilesh. Okay, Nilesh Kumar is sleeping. Drishan, is it okay now?
Yes, sir.
You get that? Kanika, is it okay? Sigma S square is equal to plim S square is equal to sigma square?
Yes, sir. Yes, sir.
Okay, so by the product rule, plim S square x transpose x into sigma square Q inverse. Thus, the appropriate estimator of the asymptotic covariance matrix of B is estimated asymptotic variance equal to sigma S square x transpose x inverse. Oh, probably. Now, this is very important now. I'm going to give you a lot of examples which you are going to do. What is it so far now that you have seen? We started with estimation. We started with the simple wireless model, the classical, what others call as classical linear regression model, CLRM. CLRM, you can call a regression model a classical linear regression model if it satisfies some assumptions A1 to A6. Assuming those assumptions are satisfied, we derive the estimator. The estimator is fine. The estimator, when you derive an estimator, wireless estimator is only for one sample that you have. But that is not the case because there's a population. You have taken one sample from a population. How can you be so confident about the estimator? This led to two properties of the estimator, finite sample and large sample. Finite sample properties, we showed that if it is unbiased, variance estimator is unbiased, and it satisfies the Gauss-Markov theorem, then we can claim B to be having some properties. B is the best linear unbiased. But then unbiasedness also have problems. The main problem is, okay, unbiasedness is also small sample properties also for finite sample properties. But normally you would expect the estimators to improve as sample size increased. That is one thing. And the second thing, more serious stuff is, this is true only so long as you are in the comfort zone of CLRM. But how long are you, practically in no situation will you be there in the comfort zone of CLRM. There will always be some problem or other. So when you come out of it, all these finite sample properties will be affected. Where does that leave you? That point takes you to the loss sample properties. Okay, I'm having a finite sample, I've done that. I hope as n tends to infinity, these properties will be satisfied. It will be consistent and the distribution will be asymptotically normally distributed, where the estimator for sigma square also will be consistent. It goes to the population parameter sigma square. I only hope, and here in this case, we distinguished between limiting distribution and normal distribution. Okay, limiting distribution to say that is a true ideal distribution, and that is our goal. So, but we have only finite distribution. So we derive the asymptotic distribution, and this asymptotic distribution as n tends to infinity will reach the limiting distribution. So that is the whole idea. Okay, that is what we have been saying so far. So you hope that as n tends to infinity, this will be the case. So always use the asymptotic distribution to pass conclusion on inference, for any inference on the parameter vector or for some other use. Okay, at this point, I would like to introduce to you this possibility. What is this possibility? Asymptotic distribution of a function of B. I have seen that we have seen this before, and I also said this before. I have calculated, I have estimated the parameter vector B. Suppose I want to calculate some other quantity which is a function of the elements of this vector B. Okay, where is that one function? Which is one example that comes to your mind, that should come to your mind immediately, is a concept of elasticity, which we discussed right at the beginning when we were discussing, remember, a digression on expectations, law of iterated expectations, conditional expectations, and all those stuff. We saw elasticity being expressed as a function of beta. It's a function of beta, and they're all pretty nonlinear functions. Okay, so suppose you are interested in such functions. You have been given the distribution of B, the OLS vector. Second point, you are defining a function in B, for example, y equal to beta 1 plus beta 2 by exponential beta 2 or beta 3 square for some reason. What you have been given the distribution of beta, what will be the distribution of the left hand side, y or something, whatever I said. That is the next topic of discussion. This is very important in econometrics. I'm going to explain in this connection the idea of a delta method. This delta method is closely related to the Taylor approximation that must have dealt in mathematics. Okay, so before you go to asymptotic distribution of a function of B, I'm introducing, that is called the delta method. I'm introducing just the revision of a Taylor series single variable. Go through it, please. The third bullet point you take down. You take down the third bullet point.
Sir, can't we just do it by Lagrangian mean value theorem or something like that? No.
What value theorem?
Lagrange mean value theorem.
Lagrangian, you should have There is Lagrangian. You normally go for
The mean value theorem, sir. Fx minus fa by x minus a is equal to.
Mean value theorem. Mean value theorem also is a thing of rather. We use the mean value theorem for proving CLT, right? This is a special Taylor's approximation for some special case, isn't it?
Yes. Yes.
Okay. So linear approximation in one variable. What is the Taylor series for multivariable? This is it.
Sir, also mean value theorem, they say that there's a point between x and a such that
No, that's also true. Mean value theorem says I'm interested in a point C in the interval AB, correct?
Yeah, exactly. Not exactly A or B.
No, not
some
exactly A or
points.
B. That is why there's not exactly A or B. But Taylor series also can be explained at a particular point, right? Or can be approximated at a particular point. For example, A equal to 0, something like that.
It's approximation,
yeah. Taylor series multivariable. Okay, now infinite differentiable function, some open neighborhood around xy is equal to AB. Now this is not what you should take down. What you should take down is this. The more compact form, understand the more compact form and take the last bullet point. I may not go beyond the first order. That is why. Okay. The second bullet point you take and the last bullet point. See the notations there. X is a small, that's a vector, A is a vector, and H is a matrix, Hessian matrix. This is the matrix of first order. Del F is equal to, that will be, so that will be the first order derivatives. H will be the second order derivative, the Hessian matrix. A useful result known as the delta method is a handy tool to approximate the probability distribution for a function of an asymptotically normal statistical estimator from a knowledge of the limiting variance of that estimator. Okay, so you have been given a vector B, you have been given its distribution. That distribution is normally distributed. Next point, now you are defining a function of B, which is a vector, it could be a vector or a scalar. Now we are interested in knowing what will be the distribution of that function. The tool that is going to help you is the so-called delta method. Okay, it gets its name from its use of calculus. For a single random variable, sample, mean, or otherwise, we have the following theorem. Limiting this normal distribution of a function. Okay, Zn minus mu, root n Zn minus mu, we have seen it goes to sigma 0 sigma square, and if Gn is a continuous and continuously differentiable function of G prime mu not equal to 0 and not involving then, what will be the distribution of Gzn? This is what exactly I was telling you. Zn is a random variable. It is distributed normally with mean 0 and variance sigma square. I'm defining a function in Zn, which I call a Gzn, which is a continuous and continuously differentiable function with the G prime mu not equal to 0 and not involving n. Then what will be the distribution of Gzn? The limiting distribution of Gzn. The limiting distribution of Gzn is this. Now my question is, can you arrive at this result using the Taylor series approximation? You tell me how. Approximation for one variable. You have to show this is nothing but the mean variance of the Taylor series approximation. Should I show or you can try?
Sir, like I did not understand what exactly we are doing with Taylor series here when a distribution is given.
We are using the delta method, not the Taylor series. Kumar. Is it Kumar?
Yes, sir. Yes.
We are using the delta method. The basis of delta method is the Taylor series. You get the point?
Yes, sir.
Now,
Sir,
this.
are we just taking gzn minus g mu is equal to zn minus mu into g prime mu, and then zn follows normal mu comma sigma square by n. So from that case, we are getting that.
First, write GZN ka Taylor series expansion. Okay, let me show the result. The proof of the delta method uses the Taylor theorem along with Slutsky's theorem. Know that the mean and the variance of the limiting distribution or the mean and the variance of the linear Taylor series approximation. So look at this. This is the Taylor series approximation. Can we say this?
Yes, sir.
Can you show that this is nothing but the mean and the variance of this? You take this down, mean and the variance of this Taylor series approximation is this. Can you show this? What will be the mean of GZN? The expected value of GZN.
Sir, G mu?
G mu, yes.
Correct.
G mu.
Next, what will be the variance of G mu? What will be the variance of GZN?
G prime mu whole square into variance of Zn, which is
minus mu. What is the variance of Zn minus mu? Variance of Zn minus mu is this. See what I have written? Now you understand the connection between Taylor theorem or the linear approximation of the Taylor theorem and the delta method and how the variance, the limiting distribution is attained. Kumar?
Yes, sir. Yes, sir. Yes, sir. Now
I'm giving you more examples. You are going to do
yes,
that. Don't worry. I have 3 examples. Okay, 2 examples I will do. 3rd example you will do. Okay, no matter how much time it takes, because this is a very important area. The multivariate version of this theorem will be used extensively in econometrics and is given below. What is a multivariate version? Limiting distribution. Okay, I'll stop here. Hello, class?
Sir, will you give all these proofs in the exam?
Who is this?
Sir, Kanika.
What proof?
Sir, sir, will you give any proofs in the exam?
I'm not going to ask you any proof, don't worry.
Okay, sir.
That's what I told you. You remember the basic rules. Basic rules. What are the basic rules? This is the basic rule. What is consistent estimator for sigma square? Is S square consistent estimator sigma square? Yes. Okay. What is this? Now, plane A square is equal to sigma square. This is the result you have to remember. Is it difficult to remember this particular result? No.
So can you please send practice questions like last time?
Oh God, who is this Kumar?
Yes, sir.
I was hoping upon hope nobody will ask this question. Now you have dropped this bomb on me. Why are you doing this to me, Kumar?
Sir, you can also tell us where from we can practice like probable questions from these topics.
I take it from many sources, Drishan. Difficult to tell you. That is precisely the reason why I'm giving you the PPTs. I hope the PPTs are useful. Last time, Kumar, Peramila, last time students were complaining. I have to read from 13 books. How is it possible? Were you not complaining, Kumar, last time?
Yes, sir. So actually, this portion of econometrics becomes slightly tough. So if the practice questions were there, so that would have been
here this portion of practice question, the delta method that I am going to explain next is very important. I'm not going to pull back any punches there. That's the first point. The second point, asymptotic properties, proof and all, forget it. Don't worry about the proof of the asymptotic properties. Do you understand, Drishan, Kumar, Kanika, Paramila, and all those other guys? You know the final result. You definitely know the difference between limiting distribution and asymptotic distribution. Given the limiting distribution, I can write the asymptotics, and the converse wise also. Given the asymptotic, I can write the limiting distribution. Okay, this is very important. And the finite sample properties, unbiasedness. How do you prove unbiasedness? Because why should you know at least the unbiasedness? Because that leads to omitted variable bias. Okay, how can you quantify the omitted variable bias? So for that part alone, concentrate on how we got the unbiasedness principles and how we got the how we quantified the bias because of the omitted variables. That is the only thing you should concentrate on the entire class. Okay, the large sample properties are only for completion of knowledge. Having done and so finite sample, asymptotic properties also have to be mentioned. That's why I mentioned. You just know what is consistency of OLS estimator, plane B equal to beta. What is consistency of A square? Plane A square is equal to sigma square. These are the two statements that you have to remember. Nothing else. The proof and the in-between things that we use in the proof, that is for your knowledge. Wherever you want to use, you can use. Understood? That makes your life easy.
Yes, sir.
Unbiasedness is very simple, that you can derive. Omitted variable bias, you should know how to quantify the bias because of omission of relevant variables. That is precisely the reason why I am saying that you should know what unbiasedness is. And those steps are very simple. Okay.
Sir, by omitted variable bias, you mean that beta hat into beta 2?
Yeah. That example that you remember, we had explained it with two simple variables.
Yes.
That is that example you have to remember. That's it. The steps leading to that. Okay, Shubham Das.
Yes, sir.
So
hello,
how
sir.
did it go today? Yeah, tell me, how did it go today? What is your experience?
So today was a bit more difficult than last year because of these prelim and these things.
No, don't worry about the prelim concept and all. Can you remember the last two statements? Plane B is equal to beta. That's
yes,
it.
sir. Yes, sir. These
Plane S square is equal to sigma square. These are the only two things, and you generally understand the conceptual ideas behind what is probability limit and how we arrive at. That's all I need to know. I'm not going to ask anything involving the proof. Okay. Now
then I followed it.
You have followed. Okay. Who is that? Oh, Rudra Narayan Kushwaha. How is it going for you? See there,
Hello.
Rudra Narayan.
Yes, sir.
How is it going for you?
It's good, sir, for me.
Okay. Roshni Roy.
Yes, sir.
So how did it go for you today? How has it been going for you?
Yeah, it is okay, sir. But as somebody said earlier, that we are having our exams and also we are getting less time to revise. So there has been.
You are a PhD student, Roshni?
No, sir. I'm a MSc student.
Oh, MSc students also face this problem. What to do here? We have to compress. You see, my idea was the following. Okay, for the entire class, I'm trying to tell you. My idea was the following. I had the hello, yeah. Who is it? Somebody trying to tell me something?
Sir, it will be really helpful if you could give us practice questions. Sir, we're clueless about what questions are going to come in the exam. So
Kanika and Kumar, for asking practice questions, 10 marks will be deducted from your midterm. Kumar, तुम्हारा भी 10 मार्क कम करेगा मैं.
Sir, already it is very tough.
You are making my life difficult, yaar.
Sir, you don't need to type,
really
sir.
helpful for every student.
मेरा भी
Yes, sir,
टाइम
we'll
नहीं है भाई.
understand your
मेरा भी
handwriting.
मुझे मेरा काम भी करना है ना. And so many meetings. अभी आज भी मीटिंग है. 11:30 को मीटिंग है. क्या करूं मैं? Okay. 10 mark deducted. Kumar and Kanika. Whoever asked the practice questions.
Sir?
Please give practice questions to make up for those 10 marks. It's very important.
Yes, sir.
लिख के भेज दूं क्या?
हाँ, sir.
Yes, sir, please write. No need to type,
Yes,
sir.
sir.
Please write. We'll understand your
Sir, we can
handwriting.
understand your handwriting.
Oh, very great. I mean, you guys have not seen me writing on the whiteboard or blackboard. 1 hour you'll say this fellow's handwriting is like terrible. Okay, check with the last guys, the last class and time series guys and all have been okay. They are condemned to live with my handwriting because I don't show the PPTs, but I send them the notes, so they are okay. The econometrics guys last time was cursing me like hell. What kind of handwriting is this? Kumar, weren't you?
Sir, yes, sir, your handwriting is tough to understand, but we will manage. I mean,
see, so they were cursing me. That's what he is admitting. Kumar, very bad of you.
No, sir. I mean, sir, you taught very well, but please give us
easy. JK said joke. I was not serious. Okay. No, don't worry. Okay. I will. Okay. The only compromise is I'll write an PCB because I may not have time to type it. I'll write some questions and send it to you. Okay. That makes you happy?
Yes, sir. Yes.
Yes, sir. Thanks a lot.
Yamini, we have been quiet these days. What's happening?
Yes, sir. Yes, sir.
Hello?
Sir, actually, I have probably concepts in the hello.
Yeah.
Sir, I have done some of these concepts in the applied econometrics. I took it as an optional, so plus I'm not getting the time to revise, so I can't really say much in the class.
You always find the typos on the slides. You are the first one to find. Okay,
Yes,
now you have been saying that. Now I started finding the typos myself. Okay.
Sir, actually,
tell me.
In the last week, we had like a lot of things. We had exams, assignments, and like it was packed with everything. And so most of us could not revise what you had taught in the previous classes. Like
Okay.
Yes, sir.
Yeah, the class. Remember, tomorrow we have a special lecture at 9:30. From 9:30 to 11, we'll spend a lot of time on the delta method. Be ready to come. Be ready to solve an example. I'm concentrating on this because you don't understand how useful this will be. And after that, I'll go to hypothesis testing. Okay. I have downloaded the attendance list. Okay, tomorrow we'll meet at the same time, 9:30. Okay.
So,
okay.
So,
yeah. Tell me.
I just have to confirm this. The syllabus for our midterm is up till today's class, right?
Yes, up till today. Yeah. Good. Yeah. And Srishti, send a mail to everyone, including me, about the special classes.
Okay, sir.
This will be besides tomorrow's lecture. Tomorrow's special. Okay.
Sorry,
Thank you.
Sir, in the second midsem, you will be asking questions from the syllabus that was covered in the first midsem as well.
Yes, it's cumulative syllabus. But you know the weightage for this, it was 0.2 for the first one. This will be 0.3 for this one.
Okay.
That is 30%. Final exam will be 50%.
Okay.
Okay. Now, thank you. The class ends now. Have a good day.
Thank you, sir.
Yeah.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.